I have 8 minutes for the talk, so let's keep it short. We want to talk about the following problem. If you type my title into your REPL, you will see that 0.1 plus 0.2 minus 0.3 is not 0. It is almost 0, it's 10 to the minus 17, but you may say, yeah, that's enough for me, that's 0. But let's say you go to a lower precision, like float 16. It was mentioned in the talk in the early morning that this is the case, that people use these half precision. You will see that this type causes really not 0. So it's already non-zero on the 5th digit right here. Why is it the case? This is not cancellation, this is rounding. The problem is each floating point number is represented by IEEE in this format, a sign, an integer mantissa, significant, and an exponent of 2 multiplied together. And this creates a finite set of possible values. And I only can store these values that are in this finite set. For instance, the set is very small. In float 16 half precision, this is just 65,000 values approximately. If my number does not fit into that set, it is defined by this IEEE standard that I've rounded to the nearest value I can represent. So in this case, 0.1 is rounded up a little bit. You can see the difference by comparing, or you can see it by comparing it like to a big float type. You see that the difference is positive, so it's a bit bigger than, a bit larger than when I represent it in big floats. You may ask now, why should I use low precision at all? And I'm really glad that the answer came already in the morning. The modern hardware for AI or for neural networks is optimized for low precision. So the GPUs, IPUs, TPUs, however it's called, work with half precision and even less, like there are techniques on 8 bits and so on. So we cannot neglect the problem right here. Can stochastic rounding fix everything now? So is everything probably correct now? The idea is pretty simple. It's a bit formulated mathematically. For every number f that's not in the set of floating point numbers, so that needs to be rounded, I have a floor and a ceiling, so like an f and a c. And the idea is I decide whether to round down or to round up by a round up probability. And this is the relative distance. So if x is very close to f, so to the flooring number, this is almost 0. If f is very close to c, so the ceiling, this is almost 1. So the probability depends on the relative distance. And then I just define the stochastic rounding by the probability q for rounding up and probability 1 minus q for rounding down. A nice effect and left as exercise for the reader is that the expected value of stochastic rounding is x itself. So in the end, the result is precise in mathematical terms. If we apply this to my title, it is 0 on average. If you want to try this out with Julia, you can do it. Milan Klöver has an awesome package called Stochastic Rounding JL, and you can do the following. The package exports the type float16SR, which is the stochastic rounding, float16 type, for instance. It also exports other types. And I put this equation here 10 times and show you the result. I use 1 over 10, 2 over 10, and 3 over 10 because I want to avoid putting in 0.1 because it was already rounded and I want to avoid that. You see the result, I get 10 different results because it's stochastic, it's random. You see it's sometimes 0, it's sometimes something positive, it's sometimes something slightly negative, but in the end, it will all be on average 0. I'm really fast. This is done in software. If you want to do this in hardware, we have also something available right now. I don't want to advertise the company right now, but you can contact Mosè Giordano. He knows stuff about it, and I also linked a talk from him in my sources in the end. Okay, so this is the pretty idea of stochastic rounding. The question is now, I'm working on numerical simulations for PDEs. Can we apply this to some real-world simulations? And this is a small reference computation, just a laminar flow, so just a Stokes equation through some geometry. And you see the velocity here. And the reference computation is done in standard precision, which is float 64, double precision. And I have the peak value of the velocity here at the narrow part, which is seems fine. If you do the same simulation with half precision, like with float 16, you get almost the same value. You see some perturbations here on the bottom, but it looks the same. But if you look at the scale, I hope you can see it, it's an 8 here and a 7 here. So the result is completely wrong. It just looks right. So we cannot do numerics in half precision. That's why we use double precision in numerics usually. But if I use it with stochastic rounding, so half precision with stochastic rounding, the type from the stochastic rounding package, the result looks way better. So it's almost the same here. We have some slight perturbations here, but the maximum value is almost the same. So the quality improved a lot. While I only have a fourth of the digits, so I have like double precision versus half precision. Keep in mind that this is one state. If I rerun the simulation, I get a different result. So it's stochastic. Some scientific view on it, I measure the velocity error. So I measure the error at the narrowest part, so the velocity, and compare it to the reference solution in double precision. So, and I have like single precision, half precision, and half precision with stochastic rounding. And what you see, that half precision and single precision and half precision with stochastic rounding behaves the same. So the error is equal, while half precision without stochastic rounding, the orange line, does something random. Pun intended, because it's not random. If you implement something now, you see, yeah, that's obvious. Let's everything do now in stochastic rounding. It's not so easy. You have a lot of challenges to face. First of all, it's slow because the package emulates this in software. Yeah, so every floating point operation needs to be evaluated, rounded stochastically, and so on. Second, you cannot use all the Julia solvers almost, because all the Julia solvers go down to like 3 sparse. So if you use a direct solver, go to some 3 sparse pack, and this is only given for double precision. So in my linear case, I just use like sparse pack, which is a pure linear solver that can solve directly solve in any number type. Float 16 has a very low dynamic, which means that large numbers tend to get infinity, because 10 to the 5 in half precision is the maximum number you can get. Otherwise, you are infinity. So if you have a finite element simulation with like penalty weights for like the boundary values, keep in mind that this will break down your whole simulation. And another part from a research point of view, like, is you cannot solve linear systems and keep the expected value of your solution, because the expected value of 2 random variables that are divided is not the same as the division of the 2 expected values. So keep that in mind. Think about this for a second. That you cannot solve linear systems with stochastic numbers and keep the expected value. I think I'm already at my end of my talk. If you watch the video, I can pause it here. I have some papers here, like it's a review about stochastic rounding, some applications for ODEs done in Julia with the stochastic rounding package, with some real-world simulations and some links to the Julia implementation. First to the software implementation and how to apply it to a hardware. So run stochastic rounding in hardware. And now I think I'm open for questions.
Thank you so much. Let's thank our speaker.